Okay, we are on the air now. Well, good evening, everyone. How are we doing? How are we doing with the practice test? Anybody taking a test this week?
50%.
Oh, you're actually doing pretty good. I would say at this point, if you're better than 25%, you're doing good. Hopefully, as the class progresses, your scores will gradually get better. Does anybody have any questions or concerns or anything that you're baffled about? Okay, if not, let's go ahead and get
No,
started.
I'm just going to have to keep studying operations.
Well, as we go through the class and as you continue reading the book, your scores will gradually get better and better. And you only have to have 75% to pass the test. So if you can consistently get 75 or better on the practice test, then you're probably ready. Okay, well, let's go ahead. Let's see. Where am I here? Okay, I'm going to mute everybody so we don't pick up any background noise and dogs barking and trains down the road. And if you want to talk, all you have to do is push the space bar on your computer and it'll act like a press to talk switch. Okay. Still getting a few logins here. But let's go ahead and get the, oops. Here we go. Okay, can everybody see this okay? Okay, I think I mentioned before that ham radio is it's a kind of a hobby that you can spend as much money as you want to. There's lots of stuff out there to spend money on, but it's not necessary. Most of the time you can get into ham radio for probably less than $100 to get started. But as you go along, you might want to upgrade to bigger and better things. But that's all we need to get us started. Just a simple handheld and inexpensive handheld will get you going. Okay, tonight we're going to talk about a thing called Ohm's Law. This is a mathematical part of the test that you're going to have to know a little bit about. And for some of you, this is going to be really simple, really easy stuff. And for some of you, it's going to sound like a foreign language. So I'm going to go really slow and really careful through here to make sure that you understand all of it. So that it'll be familiar with you on the test. Let's see, let's get the button. Here we go. Okay, let's start with a video here. And I apologize that these videos they're really kind of dark and not very professional. For some reason, when the Zoom broadcasted, it darkens the picture. Okay, I'm gonna have to stop sharing here for just a minute and then go up and pull up the video. Okay, here we go. Can you see that okay?
Okay, for this demonstration, we're going to use what we call the garden hose analogy. We actually do this quite a bit in electronics and the electrical world because sometimes the water has the same kind of characteristics that electricity does. So as you can see, I have a garden hose here and it does have water in it. So right now, I have water pressure right here, but I have no water flow because I've got the valve closed. Now if I open the valve, I'm now getting some water flow and I still have voltage here. So electricity, we have two terms, we call it voltage and current. So the voltage is like the water pressure. Think of it as pressure. The current is like the water flow. So you think of that as the flowing. And just like in water, you can have voltage without current, but you cannot have current without voltage. The voltage is the pressure that makes the current go. Okay? Now also, there's another factor involved. We call it resistance. And every circuit has a certain amount of resistance in it. So I'm going to use this valve here to represent resistance. So if we open this up, we now have voltage here. We now have current here. Now if I apply some resistance here, as you can see, the voltage is now dropping down, and the current is also being reduced as well, because we've applied some resistance here. And if we, the more resistance we have, the less current and the less voltage we have. So voltage, current, and resistance all go together. There's another factor that's also involved. It's called power. And power is actually a combination of the voltage and the current. As we open this up, okay, let's put a little bit less resistance in here. So the voltage and the current together equals the amount of power. So the amount of power is how far out there it's going. If we give it some more, let some more current go through, as you can see, we've got more power being applied. But we still have the voltage here, we still have the current here, and if we apply some more resistance, you can see the power is going to go down, the voltage is going to go down, and the current's going to go down. And the more resistance we have, the less current, the less voltage, and the less power we have. Okay? So now, these things we can all calculate mathematically. So we're going to go back inside now, and I'm going to show you some math formulas where we can calculate the voltage, the current, the resistance, and the power, because all of those things go together to make up a circuit. Okay, so we'll go back inside now.
Okay, so now back to this. Okay, this part might be a little bit confusing to you. And it's kind of had a long history, but in the electronics world, we use the letter E to represent voltage, and voltage is measured in volts. So if we say like a battery is 12 volts, okay, that's the voltage of the battery. But in the formulas, we refer to it as E. You think, why did they use E? What's that got to do with it? Well, it originated from the original term before they called it voltage was electromotive force. And then there was a guy by the name of Voltaire that came along and said, that's too complicated. Let's make it simple. So he named it after himself and called it volts or voltage because his name was Voltaire. So that part you're just going to have to memorize. There's just no real way to know how to but in the formulas we use the letter E, and that means voltage. And then the letter I represents the current, and there again you're thinking, wait a minute, that doesn't make any sense. But current is measured in amps, so we say like we have 2 amps of current. And that originated from a French word called intensité de courant, or current intensity. Some French speaking fellow way back in the beginning of time is the one who kind of came up with that term, and he named it after the French term, which is, so today we call it current, but that is represented by the letter I in the formulas. Now this one makes a little more sense. R represents resistance. Okay, I understand that. And resistance is measured in ohms. So we might say, well, I have 8 ohms of resistance, or 50 ohms of resistance, or 100 ohms of resistance. And that is represented by the letter R. And then the letter P represents power. And power is measured in watts. You know, like we might say my radio has 50 watts of power, or the light bulb is 50 watts, uses 50 watts of power. So these you're going to have to just kind of memorize. And I'm going to show you in the formulas how that we can calculate. And if you know any two of these, you can calculate all the rest of them and even more things than that, but we're not going to get that far into it. So there's a thing called Ohm's law. It's a mathematical formula. There's actually two formulas. This one here on the left, this is P and I and E. So that's power, current, and voltage. And if you know any two, you can find the third one. And then this formula uses voltage, current, and resistance. And again, if you know any two of them, you can calculate the other one. And actually, if you know any two of any of these, you can calculate all the rest of them. So now let me give you a little what we call a rule of thumb to help remember these formulas. If you remember, you've probably heard the saying, you know, to have your cake and eat it too. Well, let me give you a different one. To have your pie and eat it right. So it's PIE and EIR. Those are the two formulas. It's P over IE and E over IR. So to have your pie and eat it right. So that'll help you remember the formulas. What I would suggest when you go to take your test, on your answer sheet, you can flip the answer sheet over and use that for scratch paper. In fact, they want you to use the backside for scratch paper. They want to see your notes. So I would say as soon as you get your test and they say go, then flip your test page over and write these formulas down so that you don't have to remember them later on. So it's PIE and EIR. Those are the two formulas for Ohm's law. And I'm going to show you how those actually work. Oops, as soon as I get functioning here. There we go. Okay, so now these are the actual test questions that are in the question pool, and I'm going to show you how to calculate each one. So this question says, how much power is being used in a circuit where the applied voltage is 13.8 volts DC and the current is 10 amps? Okay, so the first thing you want to determine is what do we know? What have they given us for answers or for information? Well, we know what the voltage is. So E is 13.8 volts because they told us that right here. The applied voltage is 13.8 volts, and it doesn't matter whether it's AC or DC, it works the same. You can have the voltage can be either or, and the formula still works. And then the next part they've told us is current is 10 amps. So I equals 10 amps. So we know that they've given us that. Now, what are we looking for? What do they want us to find out? Well, here at the top it says how much power. Okay, so we're trying to determine what the power is. So P equals power, and that's what we're looking for. So if we take, here's your two formulas. Now you have to see which formula has the P, the I, and the E in it, because those are the three things we're working with. So this first one has P, I, and E. The other one does not. It's E, I, and R. Okay, so the formula is, we're looking for power. We want to know what the power is. And the formula is I times E. So you just multiply the current times the voltage, and that will tell you what the power is. Okay, so let's write the formula down. P equals I times E. So I is 10 amps, so it's 10, and E is 13.8 volts. So it's 10 times 13.8. And of course, you can probably calculate that on your head, and that's 138 watts. So that's how we calculate power. And actually, in realistic terms, there is no way to measure power. You can measure the current and you can measure the voltage, but you have to calculate the power. Now they do have watt meters that measure power, but they're actually measuring current and assuming that the voltage is a constant level, and it'll register in power. Okay, so that's the first question. So the next one is how much power is being used in a circuit when the applied voltage is 12 volts DC and the current is 2.5 amps. Okay, there again, first thing you want to do is write down what do we know? What have they given us? Okay, they've told us the voltage is 12 volts. And they've told us the current is 2.5 amps. And now, what are we looking for? What are we trying to find? Okay, they want to know how much power. Okay, so power is the unknown. And here's your two formulas again. And once again, this is the formula on the left, the P, the I, and the E. So based on the formula, see, we're looking for power, and the formula is I times E. So you just simply multiply current times voltage. So write the formula down. It's P equals I times E. And we know I is 2.5 and E is 12. So it's 2.5 times 12, which will give us 30, and that means 30 watts. So that's how you calculate the power. Okay, so how many amps are flowing in a circuit when the applied voltage is 12 volts DC and the load is 120 watts? Okay, this one's a little bit tricky. They said load. What is a load? Well, I think I mentioned last week that a load is anything that uses power. It can be a radio, a motor, a refrigerator, washing machine, whatever. Whatever uses the power, that's considered a load. And the load is basically resistance. Everything has a certain amount of resistance to it. Okay, so what have they told us? Okay, we know that the voltage is 12 volts DC, and the load, which is, oh, it's 120 watts. Okay, they told us how much wattage it is. Okay, so the load, whatever it is, the radio, the refrigerator, whatever, it's consuming 120 watts. So that's how much power there is. So what are we looking for is how many amps, how many amperes are flowing in a circuit. Okay, so we know the E, we know the P, and now we want to know what the I is. So here's our two formulas. Now this time we're going to use the one on the right because it has the E, the I, and the R in it. Oops, no, I'm sorry, it's the one on the left. That's the P, the I, and the E. Okay, so we want to know what current is, and the formula is P divided by E. Okay, so it's power divided by voltage will tell you how much current there is. So write down the formula, I equals P divided by E, and we know that P is 120, power is 120 watts, and the E is 12 volts. So it's 120 times 12, which gives us, or 120 divided by 12, I'm sorry. I'm getting myself confused here. That's why I write things down. So it's 120 divided by 12, which will give you 10 amps. Okay, so that's how much current it's going to draw with that load, whatever it is. Okay, so what is the resistance of a circuit in which the current of 3 amps flows through a resistor connected to 90 volts? Now you have to read carefully what they're really telling you. Okay, so what do we know? So we know the current is 3 amps. They told us that. So I is current. And we know through is saying flowing through a resistor connected to 90 volts. Okay, so we know the voltage is 90 volts, which is going through a resistor. So we want to know what is the resistor? What's the value of the resistor? Okay, so here's your two formulas. Okay, this time we're using the one on the right. It has the E, the I, and the R in it. Okay, so we're looking for resistance, and the formula is E divided by I, voltage divided by current. So write this down, R equals E divided by I, and we know that E is 90 volts, and I is 3 amps. So the resistance is going to be 30 ohms. 90 divided by 3 gives you 30. Okay, what is the resistance in a circuit for which the applied voltage is 12 volts and the current flow is 1.5 amps? Okay, so there again, the first thing you ask is, what do we know? What have they given us? Okay, we know the voltage is 12 volts. They told us that. And we know the current is 1.5 amps. They told us that. And what is it we're looking for? We want to know what is the resistance. Okay. So here again, there's our two formulas. So we want the one that has the E, the I, and the R in it. And that's going to be the one on the right. So we're looking for resistance. And the formula is E divided by I. It's voltage divided by current. So write the formula down as R equals E divided by I. And E is 12 volts and I is 1.5 volts. So it's 12 divided by 1.5. And that gives you 8 ohms. So R is 8 ohms in this circuit. Okay, what is the resistance of a circuit that draws 4 amps from a 12-volt source? So you have to kind of be careful. The way they word it, it can be a little confusing. But just break it down. So first of all, what do we know? Okay, we were trying to find the resistance. We have a circuit that draws 4 amps. Okay, so we know the current is 4 amps. And from a 12-volt source, so we know the voltage is 12 volts. And what are we looking for? We're looking for resistance. Okay, so we want to try to find R. So here's your two formulas. And in this case, it's the I, the E, and the R, which would be the formula on the right. And we're looking for R. We want to know what R is. And the formula is E divided by I, voltage divided by current. Okay, so write the formula down. R equals E divided by I. So E is 12 volts and I is 4 amps. So 12 volts and 4 amps of current, which is 12 divided by 4, which will give you 3 ohms. So the resistance is 3 ohms. Okay, what is the space bar up there is in the way. Let's see. Okay, what is the something in a circuit applied voltage? It's supposed to be current, I think.
Current flow.
Oh, current flow. Okay, sorry, I can't read it. Is that thing up there in the way to you too?
Yes.
Oh, okay. I know there's a way to get rid of it, but well, let's see. Let's see if this will work.
You're making it work.
Okay, I'm trying to delete that up there. Let's see.
Some kind of a taskbar.
There it is. Okay, that better? Okay, so what is the current flow in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? Okay, so what do we know? They told us the applied voltage is 120 volts, so we know. Oops, I think quit working. There we go. Okay, voltage is 120 volts, so E is 120. And what else do we know? And the resistance of 80 ohms. So we know R is 80 ohms. So what are we looking for? We're looking for current. Okay, so here's our two formulas. And the E, the R, and the I is in the formula on the right. Okay, so what we're looking for is current. We want to know what current is, which is I. And the formula is E divided by R, voltage divided by resistance. Okay, so let's write that down. I equals E divided by R. And we know that E is 120 volts and R is 80 ohms. So 120 divided by 80 is 1.5. So since it's current, it's 1.5 amps. And this really does work in the real world. If you ever put a voltmeter on a circuit, you can actually calculate it and it comes out right. It works every
Dale?
time. Yes,
Wouldn't it be 15 amps?
120 divided by 80. Oh.
Oh wait, maybe
It,
maybe not.
106, no. No, it'd be 1.5.
Sorry, never mind.
Yeah, 120 divided by 80. Yeah, if it's 120 divided by 8, it would be. Okay. What is
Okay,
the
so
current? Oh, what was that?
that's one question you got wrong on the test.
Is that one question? Oh, is this one question you got wrong?
He got wrong. He said it was
Oh, I see.
Yep.
Yeah. And that can fool you sometimes. You have to kind of double check and say, well, wait a minute, is this right? And a lot of times they will give you the answers. They'll have one answer is 1.5 and one answer is 15, which can easily throw you off. You look at it and say, oh yeah, okay, that's 15. And you look at it more carefully and it's actually 1.5. Okay, what is the current flowing through a 100 ohm resistor connected across 200 volts? Okay, so there again, what do we know? Okay, we know the resistance is 100 ohms. And we know that the voltage is 200 volts. Okay, and what are we looking for? We're looking for current. We want to know what I is. Okay, so here's our two formulas. And we want the one that has the R, the E, and the I in it. So that's going to be the one on the right. So we're looking for current, and the formula is E divided by R, voltage divided by resistance. Okay, so let's write that down. I equals E divided by R, and we know E is 200 and R is 100. So it's going to be 200 divided by 100, which should give us 2. So the answer is 2 amps. Okay, what is the current flowing through a 24 ohm resistor connected across 240 volts? Okay, so, and don't let these big numbers throw you off. They're not as harmful as they seem. Okay, so what do we know? We know the resistance is 24 ohms. And we know that the voltage is 240 volts. And what are we looking for is current. How much current's going to flow through there? Okay, so here's our two formulas. And the formula that has the R, the E, and the I in it is going to be the one on the right. So we're looking for I. We want to know what the current is. And the formula is E divided by R. So it's voltage divided by resistance. So let's write the formula down. I equals E divided by R. So E is 240 volts and R is 24 ohms. So it's 240 divided by 24. So the current would be 10 amps. Okay, what is the voltage across a 2 ohm resistor if a current of 0.5 amps? Now, so you have to watch this. This is 0.5, so it's a half an amp flows through it. And sometimes, and they'll give you one of the answers will be 2 ohms with 5 amps. Okay, so what do we know? Resistance is 2 ohms and current is 0.5 amps. So it's a half an amp. And what do we want to know? We want to know what the voltage is. Okay, so here's our two formulas. We have a R and an I and an E. So that's going to be the formula on the right. And we're looking for E. We want to know what voltage is. And the formula is I times R. Just multiply the I times R. Okay, so write the formula down. E equals I times R. So I is 0.5 and R is 2. So 0.5 times 2 is 1. So that'd be 1 amp. What is the voltage across a 10 ohm resistor if a current of 1 amp flows through it? Okay, so there again, what do we know? Well, we know resistance is 10 ohms, and we know that the current is 1 amp. So we want to know what is the voltage? How many volts is that? Okay, and here's our two formulas. We want the one that has the R, the I, and the E in it. That's going to be the one on the right. You notice most of these are from the right. I think there was only two from the left. Okay, so voltage is E, and the formula is I times R. So we're going to take, let's write down the formula. E equals I times R, and I is 1, and R is 10. So 10 times 1 is 10. So it'd be 10 volts. Okay, what is the voltage across a 10 ohm resistor if a current of 2 amps flows through it? Okay, so what do we know? Resistance is 10 ohms, and we know that the current is 2 amps. Okay, so I is 2, and what do we want to know? We want to know what the voltage is. So here's your two formulas again. We want the one with the R, the I, and the E in it. That's going to be the one on the right. And we're looking for voltage. We want to know what the volts are. So E, and then the formula is I times R. You just multiply the 10 times 2. Like I say, most of these you can probably just do in your head. Okay, so write down the formula. E equals I times R. So I is 2 amps, and R is 10 ohms. Okay, so 2 times 10 is 20. So it'd be 20 volts. Okay, so you have now seen every question on the question pool that has to do with Ohm's law. So if you can do all of these questions here, you'll be able to ace it. No problem at all. Okay, let me just give you an extra credit one. This is not on the test, but just I want to see if you can figure this out on your own. Okay, if you plug in 5 light bulbs, and they're each 100 watts, into a single power socket, how big of a circuit breaker do you need? Okay, I'm going to give you just a minute, see if you can figure that out on your own. And then I'll walk through it and see how you did.
Is this
Okay.
a 120 volt AC circuit or a 12 volt DC circuit?
Well, it doesn't say, but it just says it's plugged into a power outlet. So we would have to assume that's a 120 volt outlet in your home. Okay, everybody come up with an answer? Okay, let's walk through it and see how you did. Okay, what do we know? The power is 500 watts. So there's 5 light bulbs. They're each 100 watts. So that'd be a total of 500 watts of power. Okay. And the voltage is 110 volts, a standard AC power in your home. And actually that voltage can vary anything from about 100 to 130 volts. They typically say either 110 or 120. And so what we want to know is, if we want to know what size circuit breaker, So we need to know how much current, because circuit breakers operate on current. So we want to know what is the current. And here's your two formulas. And this one we're using the P, the E, and the I. So that's going to be the formula on the left. And we're wanting to know what is the current. So we want to know what I is. And the formula is P divided by E. So it's power divided by voltage. So if we write down the formula, I equals P divided by E. Okay, power is 500 watts and voltage is 100 watts. So it's going to be 500 divided by 100. And that should give us about 5 amps. Now you notice that I just rounded it off. You know, even the house current, typically they're 110 to 120. I just rounded it off to 100 because all we just need to know what's close to it just to make it easy. So if we figured 100 volts and 500 watts, so it's going to draw roughly about 5, maybe 5.5 amps. So typically you would use a circuit breaker. They normally rate circuit breakers about double what you actually use. So if you've got 5 amps circuit, you're probably going to run a 10 amp circuit breaker. So that's how you can calculate what size circuit breaker you need in your house.
Why wasn't it 120 volts instead of 110?
I just rounded it off. I just made it 100 to make the calculation easy.
No, I mean, I know you just explained that, but
Oh,
wouldn't it have been 120 over on the left?
it depends on who you talk to. It can be 110, 120, sometimes 130. Because it varies quite a bit from one house to another. Or from one time of day to the other. You might measure 100 volts today and be 130 volts tomorrow and 120 volts the next day. Most people refer to it as either 110 or 120. That's kind of a standard term for it.
Okay, but if I had taken 500 divided by 120 and came up with 4.16, that's not really wrong.
No, it's correct.
Okay,
Yeah.
thank you.
So if you come up with 4.16 amps, and like I say, typically most circuit breakers either come in 5, 10, 15, 20 amps. So the next size up is probably going to be a 10 amp circuit breaker. Okay, so that's just a typical or practical application of Ohm's law, something you can actually use in your home and determine, or sometimes you want to know, well, how much current am I drawing? Well, we can find out. Find out what the power rating is. Let's say your washing machine, for example. If you look, it'll tell you how much power it uses. Calculate the power and the voltage and tell you how much current it is and how much usage there is. Okay, so any questions on Ohm's law? Anything that doesn't make sense to you?
Hey Dale, I have a question about ohms.
Yes.
So I've always known ohms in speakers.
Right. Uh-huh.
Okay. So, if you're talking about speakers, they'll say they're stable to so many ohms.
Right. Uh-huh.
And that is a changing number, I guess, based on, say, the watts or how many speakers you have. Is that correct?
Well, actually, speakers are kind of interesting. If you put an ohm meter across the speaker, it'll measure almost a dead short. But it's what we call impedance rather than resistance. So the impedance of a speaker is at audio frequency is about 8 ohms. And it can vary depending on the frequency of the audio. It can vary slightly up and down. But generally the impedance of a speaker is about 8 ohms. Or you can get them 16 or 24 ohms or whatever size, they come in different sizes. And then there again, if you put two of them in parallel, you're actually going to divide, because if you put an 8 ohm in parallel with an 8 ohm, you're actually going to come up with a 4 ohm load. So it's going to put a 4 ohm load on your amplifier, which in some cases can be harmful. You just want to be careful about stuff like that. But yeah, speakers are a little, they're kind of funny the way they, what they're rated and what you actually measure with them.
And
So-
if you put them in series, then you double it.
Right. Uh-huh. If you put them in series, then you'll have 16 ohm load. Or sometimes what I've seen people do is take two speakers and put them in series and then put two other speakers in series and then put those two in parallel. So you end up with a total of 8 ohms. You know, if you put two in series is 4 ohm, or two in series is 16 ohms and two in series is 16 ohms, and put those two in parallel comes out at 8 ohms. So you can actually drive 4 speakers that way. Okay, did that confuse you or did that help any?
That's great, thank you.
Okay. So now that
Right.
we've gone through all that, and like I say, this video will be available if you want to pull it back up and review it again.
Okay, so Dale, on the video,
Uh-huh.
when you review it, can we stop it and look at the stuff at any point, kind of like a YouTube video where you can just
Yes.
stop it?
Huh? Yep, you
Yeah.
can stop it and look at it, or you can back it up and review it again. Well, yeah, I think you can stop it online. I know if you download it, you can definitely, I mean, it becomes just like a YouTube download video. Where you can stop it, back it up, reverse it, play it again. I think you
Okay.
can do that online too.
No, I haven't done any of this stuff since high school, man. So I think
Yeah.
I need to review it for a while.
Yep, I understand. And like I say, to some people, this is going to be like a foreign language. If you don't use it all the time, you can forget it real easy. And actually, once you get your license, you'll probably never use it again, and you'll forget it again, and just like you did the first time.
That's true because I got my tech license back in 2000, I think it was.
Uh-huh.
In that time, and yeah, I haven't used anything since then. So
Yep. And actually, I work in two-way radio communications. I've worked in it for 40 years, and rarely, very rarely have I ever used it. And just, I mean, we install radios and program them, set them up, and there's just no need for all that. But it's a good thing to know.
it's like doing algebra, or and then learning quadratic equations.
Yep.
Why?
Yep.
Yes, thank you.
Yep. In fact, when I went to school, we got into calculus and trigonometry and all that kind of stuff, and I have never used it, not once, in my whole career.
I use trig quite a lot with my job, but
Oh, did you?
that was pretty good. Yeah.
Yeah.
Drafting, engineering, and
Uh-huh.
designing gear trains and stuff like that. So you had to calculate the depth of the gears and the ratios and all that. So it was
Uh-huh.
pretty interesting. But
Yeah.
yeah, quadratic equations, nah, that's crazy.
Well, I suppose if I was an engineer designing radios or designing circuits, then I'd probably use it. But just for everyday use out in the world, you'll probably never use it again. So all you need to do is just learn it enough to pass the test, and then you're done with it. Okay, so should we move on to something a little bit lighter? I don't want to, spend the whole class on heavy duty math and stuff. So let's look at some other things that are a little more interesting, maybe. Okay, so components. There are going to be some test questions on components. Basically, the only thing you need to do is be able to identify what a component is. You don't really have to understand the circuit. You don't have to understand what it does or anything, as long as you can just identify it. But I'm going to show you kind of what some of the components do and how they work and so forth. Okay, so I got another video here. Let's see. I found that I have to load these videos separately. You can actually put a video in the presentation, but I found that Zoom, it doesn't handle it real well. So I have to pull the videos up separately. Okay, let's see. I close all these different things. Let's see. 3B.
Okay, for this.
Okay, so in this video, I'm going to show you actually how a transistor works. And you don't need to know this for the test, but I thought it might be interesting. You might like to see how a transistor actually does what it does. I like to throw in some interesting things that just something you might like to see. Okay, here we go.
Okay, for this demonstration, we're going to go back to the garden hose analogy, and I'm going to show you how a transistor works. In a circuit, we're going to have a transistor, which is going to be represented by this here. We have current that flows down through the transistor, which goes to ground. This is the supply voltage. And a transistor, you can electronically turn it on or off or partway on. That's why they call it a semiconductor, because you can turn it on a little bit, or a little bit more, or a little bit less. So if we turn this on more, you see we get more current flowing through the transistor. And we can turn it on less, we get less current. Now in a transistor, we can actually very quickly go on and off and on and off and on and off, and see what happens to the current as we're electrically turning it off and on or partly on. It's changing the current flow through the transistor. So we can actually electronically cause this to switch or to change levels. So by doing that, we can change the amount of current. Now if we have a resistor back here, the pressure right here is going to vary as we vary the conductivity of the transistor. So by putting an electrical signal in here, we can cause the pressure here to vary. And that's what we're trying to do, is by putting this little bit of signal here, we get a bigger signal out here. And that's how a transistor works. Think of it as an electronic valve that controls the flow of current through a circuit. So if a transistor can be turned off completely, or it can be turned on completely, or it can be anywhere in between. And like I said, that's why it's called a semiconductor, because you can turn it on a little bit or a little bit more, or you can turn it all the way on, or you can turn it all the way off. And that can all be done electronically. So once we go back inside, I'm going to show you how that works in a circuit. But think of the transistor as just like a valve in a water line. It works the same way. So let's go back inside and I'll show you some pictures and some diagrams of that.
Okay, let's go back to where we were. Okay, so let me talk just a little bit about transistors, and I'm going to kind of show you how transistors actually work and how they do what they do. Most transistors have 3 legs on them. Some have 4, but most of them are just 3. Okay, in a circuit, this right here is the, oops, this right here is the transistor. That's the circuit diagram symbol of a transistor. Okay, so we have, see, this is our voltage supply up here. So the current flows down through this resistor, this squiggly thing, that's a resistor. And then it flows into the transistor and comes back out the transistor. And there's a small value resistor down here, which goes to ground, which is the other side of the power supply. So electronically, we can take this leg right here and we can vary it to vary how much current flows through the transistor. Now, because there's a resistor up here, as the current changes in the transistor, it's going to change the voltage right here. As you draw more current, the voltage is going to go lower. If you draw less current, the voltage is going to go higher. If you turn it off completely, then it'll come all the way up to the power supply voltage, whatever it might be. So we're going to electronically control that. And we've got 2 resistors. One comes down here and ties to this leg and then goes down to here and to ground. And what this is going to do is going to provide some voltage, but not the maximum. And we want to basically turn this transistor on about halfway because we want it to be able to go both positive and negative. Well, you can't really go below ground. So if we got it turned on about halfway, we can make this voltage increase or we can make it decrease. And we're going to put a signal in here. Now this component right here is called a capacitor. And a capacitor will pass AC current, but it will not pass DC. And the reason we put it here is because we want this voltage right here at a specified value. We don't want it bleeding back into here, which is going to mess up the bias of the transistor. So we put a capacitor here to block the DC voltage, but it allows the AC voltage to flow through it. So if we have a signal here, this could be audio, for example, and it's represented by this what we call a sine wave, and it's constantly fluctuating. It goes to positive and then negative and positive and negative. And if we send this into here, it's going to go into here and it's going to ride on top of that DC voltage. So as this goes positive, it's going to cause this DC voltage to go more positive. And as if this goes negative, it's going to cause this to go less positive, but it won't go negative. It's just going to reduce it some. So it's going to cause the transistor to turn on. As we go positive here, it's going to turn on, which is going to cause this voltage to go low. So the voltage is actually going to come down like this when this one's going positive. And then when this goes negative, the transistor conducts less, so it allows more voltage over here. So we actually get the same signal here, comes out over here, but look at the size difference. See how big this is? It's this tall here, and look how big it is over here. So what we've done is we've actually amplified it. This is a one transistor amplifier, probably just an audio circuit, very simple. And by feeding a small signal into here, we can get a bigger signal over here by causing this transistor to vary in how much it conducts. So that's basically a simple amplifier. Now transistors don't amplify a huge amount. They just amplify a little bit. So if you want more gain, you can put more of these circuits together. We can take this circuit, add another circuit just like it, and amplify it some more, add another circuit, and amplify it some more. And each time you go through a transistor, it amplifies it more and more until you get to the level that you want. So here's a diagram. This is just a simple circuit here. And it's basically the same thing. We have a transistor right here. Now here they're just using a single resistor for the bias. But the current flows down through here, through this resistor, and it flows through the transistor to ground. And we can vary how much that transistor conducts. So by putting an AC signal here, we can cause this to fluctuate and produce a little bit bigger signal here. Then we can go into the next transistor and it's going to amplify it some more, and then go into the next transistor and it's going to amplify it some more. And then this is connected to a speaker over here. So you can take like a microphone, for example, here, amplify it 3 times and have it come out a speaker there. But you can put as many transistors as you want. Each one's going to amplify it a little bit more and a little bit more until you get to the level that you want it. So that's basically, in very simple terms, how a transistor works. And these other, see, a transistor can't do anything by itself. It has to have other components to support it. And these are resistors. These are those resistors we've talked about, and capacitors. And those are the 2 main components that are used in amplifiers. So here's this is a component that's called a diode. And a diode basically will conduct in one direction, but it will not conduct the other direction. So if we have current that flows this direction through here, it will conduct and the current will come out over here. But if we have current that's flowing back this direction, it will not go in the reverse direction. So if you have a sine wave over here, you're going to get a half a sine wave over here, only the positive half. Sometimes these can be used for converting AC power into DC power. Because it only passes the positive cycle of the power, and then we put filters on it to filter out all the bumps in it. But diodes can be used for a number of different things. And an actual diode, you can identify it by it has a stripe on one end. This is called the anode. This is the back end of the diode. And this is called the cathode, which is the top end, which is the output of it. And this band here identifies where the cathode is. You have to know which direction to put it in. And here again, this is a band that shows what direction it goes. Okay, this is a thing called integrated circuits. We usually refer to them as ICs for short. And an integrated circuit is where we take a whole bunch of components and squish them all down into a very tiny compact size and put them inside one of these little packages. And of course, there's multiple inputs and outputs for various things. But inside one of these IC, and there's hundreds and hundreds, even thousands of different kinds of ICs that for different purposes. And, you know, some of them are audio, some of them are RF, some of them are digital, some of them are for all kinds of different purposes. But it's basically just a complete circuit in itself. So you only have one component to put on the circuit board. A typical, this is just a simple, what we call a 2-input audio amplifier, just a very simple circuit. And all of these components will be inside one of those ICs. And up here we have, see, this is the VCC, that's your power source. We have the ground down here. This one has 2 inputs. There's a positive input and a negative input. It's what we call a differential amplifier. You're amplifying the difference between this and this. And then the output is over here. And again, there's lots of transistors in here. And this is a simplified circuit because, see, this is all copyrighted and they don't want people copying their circuit or their design. So they're not showing you everything. In fact, you see these little look like figure 8 type things here. Okay, that just tells you that is a component, but they're not telling you what the component is because they don't want you to be able to duplicate their circuit. So here again, there's a component, there's one here, and they're all over the place. And they're showing, you know, the different transistors and amplifiers and so forth. But that is what we would call an integrated circuit. It's an IC. And ICs are very, very popular because you can eliminate a whole bunch of components that would have to be on the circuit board and just put it into one nice, neat little package, and you plug it in and solder it, and then on to the next thing. Okay, some ICs are actually very small. There's a lot of them even smaller than that. If you look inside your radio, if you have a portable, like a Bofeng radio or something, the ICs are so small you can hardly even see them. But it's a whole complete circuit, probably that circuit we just saw, you know, something like that in a package that looks like that. Okay, there's another component called an inductor. An inductor is the exact opposite of a capacitor. An inductor will pass DC current real well, but it does not pass AC current very well. It pretty much blocks it. And the inductors can be used for a lot of different things. A lot of times they're used for filters, like this one up here. This is probably a filter in a power supply because we want the DC current to pass through, but we don't want all the noise and the other stuff in the process. We want to filter that out. So they use these inductors for that. This looks like it could be a tuned circuit. Sometimes you can use it for tuning. And here's a very small value one here. Could be used for any number of things. And here again, this is probably a tuning one. So, but that's called an inductor. It's basically just a coil of wire is all it is. Okay, let me show you a video. Oops, let's see. Here we go. And in this video, I'm actually going to show you some components, show you what they look like. Maybe talk a little just about what some of the components do. Okay. Looks like we're running a little late tonight.
What I'd like to do now is
Wish there was a quicker and easier way to do it, but I haven't found it yet. It's not one that works well. Okay, here we go.
Okay, what I'd like to do now is show you some of the actual components that we've been talking about. I've got here, these are transistors. These are some actual transistors. There's various types, various sizes for various functions. This transistor over here is generally used in a power supply. They're designed for high current, high power. These type, like this transistor right here, this is a power amp. RF power amp out of a radio, probably about a 50-watt power amp. This is probably a driver for the power amp. These are a little bit higher power than some of the others. This is a very low power RF type transistor. Here's one with a heat sink on it. And these are just small ones. This is probably a receiver of some type, maybe audio. So those are just some samples of some transistors. Now let me show you what, if you look inside your portable radio, this is probably what you're going to find. That right there is a transistor. See that little tiny square? That's what they look like inside portables. Here's a bigger transistor, probably a power amp type transistor for a portable radio. Some of them get quite small. So just wanted to give you a little bit of show and tell. Let me move this out of the way. And okay, these are some diodes. Diodes are used in all kinds of circuits. This is, again, this is probably out of a power amp or a power supply. It's a very high power. There's a heat sink on the back. These are typically general purpose type diodes. Could be used for signaling. This is a protection diode. This is used for spike suppressions. And there again, inside your portable radio, this is what a diode looks like in the handheld. They're very tiny. We call those salt and pepper components, and you can see why. Okay, let's clear the board, and we'll. Okay, these are in capacitors, and again, they come in various sizes and shapes for various purposes. These are probably out of a power supply type thing. They're generally used for filtering. That's what gets the hum and noise out of your power supplies. This is probably for signaling. This is a very small value capacitor. And these are like RF type capacitors used in power amps and so forth. These are kind of high voltage capacitors used for filtering. This is a capacitor out of a power amp. As you can see, well, you probably can't see it, but this is all made out of metal, and it's designed to go on a heat sink for high power transistors or high power transmitters. And again, inside your portable, this is what a capacitor looks like, a tiny little square right there. Here's another one. This is another capacitor. And here's a little bit bigger one. Okay. I don't want to spend too much time on this, otherwise you'll probably get bored with it. But I just wanted to show you what these components actually look like. This is called an inductor, sometimes referred to as a coil. And basically all it is just a coil of wire. It's usually wrapped around something. This is a tuning coil used for tuning either a transmitter or a receiver. And if you take the shield off, inside you see there's a coil of wire in there. And there's usually a ferrite rod that you can tune up or down for tuning purposes. And this is another one. That's another one used for tuning. And again, inside the portable, this is actually a coil of wire, a tiny little thing there. And here's one that's even smaller. I don't know how they do that, but somehow they managed to make them with very small, very tiny components. And okay, here's the resistors we've been talking about. Resistors are used a lot in circuits for various functions. Here's a little bit higher power one. This is typically a 1/2 watt resistor, that small one right there. This is probably about a 5 watt or a 10 watt. Here's a 20 watt. They're designed to handle more power. Here's about that's probably about a 1 watt resistor. And these are, just like we had talked about earlier, they're used in provide resistance in a circuit so that we can operate the other components. And inside the portable, this is what a resistor looks like, that little tiny square right there. And if you think it's hard to see, you ought to try soldering one. Okay, let's move that out of the way. And this is what we talked about, those integrated circuits. Remember how you can put a whole bunch of transistors inside of a box? This is probably a small microprocessor. You can see there's about 10 legs on each side, so there's about 40 connections to this. It's a microprocessor. This is a standard integrated circuit, probably for audio processing or for an amplifier. There's typically about 14 legs on them. Those are very common, used in a lot of things. This is a microprocessor, probably the type you'd see in a computer or a large radio. And there's probably 200 pins on there. You probably can't see them, but these are actually contact pins here. There's rows and rows and rows of them. And this is designed to set down on a circuit board in a very precise location, and they put a clamp to hold it in place. And there's probably, I would say, 3,000-4,000 transistors inside one of those microprocessors. And then inside your portable radio, this is a small integrated circuit. Here's one that's even smaller. I think this is a 6-pin, but used for various functions. Sometimes they're referred to as a chip. A chip because the way they're manufactured on a silicone, it's a tiny, tiny little square piece of silicone that looks like a chip. So they kind of got the nickname of, a lot of people refer to them as chips. But they're ICs, or integrated circuits. And let's see. Okay, this is another component. If you can see it, this is a transformer. And I want to show you how a transformer works. Remember when we talked about our class last week, I think it was, or the last session? Remember we have this coil of wire? Okay, that coil of wire is called an inductor, or sometimes just referred to as a coil. And if we run electrical current through there, we can actually create a magnetic field. Now, if we were to take another one and put it right next to it, this one will actually create a magnetic field, and that magnetic field will then induce a magnetic field into the other coil and cause electrical current to come out the other side. So what's the purpose of this? We can actually change the ratio of the turns. This has about 100 turns on it. And remember, this one had about 50 turns on it. So if I put the 50 right next to the 100, that's a 2-to-1 ratio. So if I put 110 volts into here, I'll get about 50 volts out here. And a transformer, that's what it does. It changes the voltage from, we can go from high to low or even low to high. We can put 50 volts in here and we'll probably get 100 volts out of here. And that's what a transformer does. We typically, most applications, you'll put 110 volts in and you get about 12 volts out. And this one, you can actually see the 2 windings. See this winding right here? Okay, that's what we call the primary. That's the 110 volt side. And this side over here is called the secondary. That's the output, which is probably about 12 volts. And transformers are kind of heavy. They're wrapped around iron. This is an iron casing. The iron helps keep the magnetic field enclosed so that we don't lose a lot of energy of the magnetic field going out into the atmosphere. So that's how a transformer works. And I wanted to show you some actual circuits. This is the inside of a Kenwood portable radio. You can see some of the components in here. This right here is the microprocessor circuit. This is where all the computing is done. This is the main processor right here, and there's about 25 pins on each side. So there's about 100 pins there, 100 connections on the IC. This one is probably an audio processor. It's kind of long and thin. There's about 10 pins on this side and 10 pins on this side, so it's about 20 pins connecting there. These are some supporting ICs to help run the processor, but most of the microprocessing and controlling is done right in there. And then if we go over to here, this is the actual circuit where it generates the audio, does the amplifying and so forth. This right here is called a crystal, and we're going to talk a little bit about crystals. And then over here, these are some other supporting components. And if you see these little tiny things right here, this one, this one, this one, those are resistors, capacitors, transistors, diodes, and all kinds of components in there. And as you can see, there's a bunch of them. They're all matted in there. It's very, very difficult to do those by hand. These are all assembled by machines because of the precision involved. So let's see. If we get up into here, this is the actual audio amplifier circuit. This is where all the audio is produced and amplified. Oh, actually, I'm sorry. No, that's not. This is actually the transmitter circuit. This is where the radio frequencies are produced, the audio is injected and processed, and this right here is the power amplifier. There's probably 2 or 3 large transistors in here, and this is what generates the 5-watt output for the transmitter. And then if you go over on the other side of the circuit, this is kind of the back side of where the processor is. This is just an open spot for an accessory board that can be installed. These are the filters for the receiver. This is another crystal. Most radios have at least 3 crystals in them. There was one on the other side, there's this one, and this is up here is also a crystal. This is probably part of the receive audio circuit here, where all the receiver comes in and it's processed. This up here is the audio portion. You can see some of these coils that we had talked about earlier. These are tuning. These are for tuning the receiver. Oh, this is the transmitter, I'm sorry. And this process goes into here, and this is the back side of the power amp for the transmitter. That's the volume control there, and this is the speaker mic jack. So that's what the inside of a radio actually looks like. And if any of you have any of these Bofang radios, you'd be amazed how similar they are to a Kenwood portable. This is actually an older circuit, an older model of radio. But there again, you can see the microprocessors. They were not nearly as big back in those days. Here's some of the capacitors. They're a little bit bigger. Here's a crystal. And again, on this side, you can see a lot of these small components. These are small, but they're not as small as the other one was on the Kenwood. Over the years, they've shrunk them down, gotten smaller and smaller. But if you ever have to fix one, trying to change one of those is a real challenge. This is actually the receiver out of a pager. You know, if you've ever been on a fire department where you have pagers, this is the microprocessor. Oh, sorry, I lost our signal. These are some of the components. Those are some inductors there. And these little salt and pepper components. Here's the crystal. This is the channel crystal. And some of the other ICs, there's small ICs in here. This is actually out of a mobile radio. This is an older model. But there again, you can still see some of the ICs in here. The components are much bigger. These are what we call through-hole components, where there's actually a hole in the board and the leads go through and you solder it from the other side. And the microprocessor, you can see it's not nearly as big as what the new ones are. And the crystals back then were much bigger than they are now. And there again, there's not a lot of components. This is mostly solder connections on this side. You see a few in here, but that's some of the older technology. And this is another older radio, not very much surface mount. These are all through-hole components. And there again, there's the microprocessor. This is for processing the various functions. And on the back side, you see a few components over here, but not many. There's some right there and a few here, but these are mostly solder connections. So we've come a long ways in those days. So let's go back to the presentation. I just wanted to kind of show you some of the components and what they look like.
Okay, well, I apologize. We're running way late tonight. Let's see if we... I think that was the last video. Okay, so let's wrap it up and we'll kind of hurry through it a little bit. Okay, this is that transformer I was talking about in the video. And a transformer basically converts voltage. You can either convert it up or convert it down. Typically it's like 110 or 120 volts in, and you get about 12 volts out. That's what we use in power supplies. But there again, all you have to do is just be able to identify what it is. These are power transformers. You've probably seen these around town. Like up around your house, you probably see these big cans hanging up on power poles. Those are transformers. Because the high voltage lines that feed these are, I don't know, they're like about 4,000 volts on these high voltage, and you don't want to run 4,000 volts into your house.
Yeah, a lot of them are 13,000 volts.
Yeah, 13. Thank you. I couldn't remember what the actual voltage. But yeah, like 13, 14,000 volts. So they feed those into power transformers, and then you get your 110 or 120 volts, which then feeds into your house. But that's a transformer. That's what that is. That's what it does. Here's a type that sits on the ground. You've probably seen these in big buildings, commercial buildings, factories and stuff. It does the same thing. It's just taking that 13,000 volts and dropping it down to 110 or 220 volts. These are what you see at big substations around town, because the main power lines that carry power across town, they're like 40,000 volts, and they feed it into these transformers, which drops it down to about 13,000, and then these drop it down to 120. So that's what a power transformer does. Vacuum tubes, I don't think there's any questions on vacuum tubes that I don't remember, but there's a lot of ham radio people that still like to play with the old vacuum tube radios. Those are classics, and they're in great demand. So I'm not going to spend much time on vacuum tubes, but basically a vacuum tube does the same thing that a transistor does. There's lots of different kinds for different purposes and so forth. Now, as far as the test goes, this is what you're going to see. There's going to be a picture like this with the various components have numbers. And the test question is, component number 2, what is it? And they'll give you 4 choices. Well, this is that transistor. It's actually called a bipolar transistor. It's just kind of a basic everyday transistor, not anything special. There are other specialized kinds of transistors. This squiggly line here, that's a resistor. This number 5, this is actually a ground connection. What they do on schematics is, a circuit has to be a complete circuit. Well, you can see by this drawing, there is no complete circuit. This is the battery here. It feeds up into here, and where does it go? Well, all of these ground points all connect together to make a common connection, but they don't draw it. They just say this is ground, this is ground, this is ground. So the current actually flows up through the bulb, down through the transistor, and back to ground, which goes back to here. This is a picture of a battery. This is what a battery symbol looks like on a schematic. This is a lamp or a light of some type. But all you have to do is just identify what it is. Just be able to say that, that's a transistor, that's a resistor. Here's a little bit bigger circuit. This is an AC power connection here. This is an AC plug. This symbol is a fuse. There's actually different symbols used for fuses. This is a switch, an on-off switch. And this one right here is on a schematic. That's that power transformer we were talking about. This represents the coil of wire on one side. This represents the coil of wire on the other side. And it converts, in this case, you're taking 110 volts, converting it down to 12 volts. This is a diode. This is what it looks like in a schematic or in a circuit. And a diode just conducts one direction. And that's a lot of times what we use to convert AC into DC. Because this is alternating current, well, only the positive side is going to go through. So you're going to get DC on this side. And then this is a capacitor. This is probably used for filtering. That smooths it out so it's not so bumpy. And a resistor. Now this is a diode with, see the little arrows pointing out? That's actually an LED. It's a light emitting diode. That's what the symbol looks like on a schematic. This is a variable variable resistor. It's one that you can adjust. And this one is a diode actually in the reverse direction. It's called a Zener diode, and it's used in regulators. The Zener diode, if you put positive voltage here, it will not conduct, but at some point, the Zener will break down and start conducting. And a lot of times these are used for regulators. Once it reaches a certain voltage, it starts conducting, and it won't let the voltage go any higher. So that keeps it a constant voltage on the output. And sometimes they're used for protection too. If the too much voltage, this will short out and blow the circuit breaker. But that's all you need to do, is just be able to identify what they are. Here's another circuit. These are all diagrams from the test question pool. This is a variable capacitor, means it's tunable, it's adjustable. This is another variable capacitor. This symbol up here, let me get rid of this. This symbol up here is what an antenna looks like on a schematic. And this is a variable inductor. It's an adjustable one. It's one that's probably used for tuning. Oops. Okay, there's a thing called parallel circuit and series circuit. I don't think there's any test questions on it, but at parallel, remember that question I showed you about the 5 100-watt light bulbs? Okay, if you saw that on a schematic, this would be a 100-watt light bulb, this is 100 watt, this is 100. They're all connected to the same outlet. So that would be considered a parallel circuit. So the same amount of current would flow through each resistor or each load. This is a series circuit where the current flows through one and then through the next one and through the next one, which can be used in some applications too. If you remember, many years ago, they used to have Christmas tree lights. And if one light bulb went out, the whole string went out. Well, it's because they're in series. The lights were strung, so the current flows through one light bulb, then it flows through the next and through the next. So if this one goes out, then these won't work because the circuit's open. But there are applications for series circuits. And these are just various types of components. You don't really need to know these for the test. This is a different type of transistor. It's called a JFET. This is another JFET. They're used in special applications. Anyway, we're kind of late on time, so I'm gonna kind of skip over that a little bit. Okay, well that's all I have for tonight. Sorry it took so long. Went a lot longer than it should have. Let's see. The homework assignment, and I'd like for you to continue taking the tests, the practice tests. The more tests you take, the more you're going to be familiar with it, and the more you'll be able to pass the test easier, I guess. Okay, and the homework assignment for this week is Chapter 7, Licensing Regulations. Now, these chapters, you need to know them fairly well because the largest part of the test is going to be on rules and regulations. So make sure you understand that and make sure that you can look at the test questions regarding the rules and regulations. Okay, well, that's all I have for tonight. Let's see, are we still, where am I? Okay, don't know how I got into this, but I don't know how to get out of it. Oh, there we go. Okay. So the screen sharing has stopped. Okay. Okay, so that's all I have for tonight. Any questions? Anything that and like I say, this video will be available. And I'll send it out. I'll send out the links to everybody later tonight, so you can go back and review it if you want to. So anything else before we wrap it up tonight?
You had mentioned sending out the Google, all the rest of your videos.
Yes. In fact, I think what I might do is I'll download this video and put it on Google Drive, and I'll send you the links to all three of them, all three of the classes. You can review any or all of them.
And the pool of questions from prior years, like the last 4 years, the entire big pool, that whole thing changes, or do just the questions they choose?
Some of the questions are the same, but a lot of them have changed. In fact, I think I sent out the current question pool. Was it last week or the week before? Did you get that?
Yes.
Okay. Yeah, that's the current one that you want to use now. And if you have an older book, the book itself doesn't really change. It's just the question pool that changes. So you can use an older book, just use the current question pool is all.
Okay, thanks.
Okay. I'm gonna go ahead and stop the recording.
Thank you, Dale.